to record. I'm not sure if all the signs are correct, but that looks close. Yes, please expand and combine. Ooh. These all feel like really close. Okay, I'm just gonna get going on the explanation of it, I guess. Yeah, no, like I don't think I have like exactly correct answers, but these look pretty close. No, I'm saying expand A, Ivan. And then combine it into one fraction. Okay, so like what ideas did people have? You look at the forces that are opposite tension. Okay, so there's an upward force of tension here. Okay, so
Louis, you're raising your hand? I'm sorry, Louis is raising his hand. What's up?
what's up? Do you have anything to say? No? Okay. So I like that idea. So what forces are opposite tension? Okay, no, first of all, what is the system that you chose in order to analyze the forces? Substitute two boxes, okay. So if we take the system to be our two boxes, right, then what forces are acting on the two boxes? Well, there's gonna be gravity. There's gravity, and because you did not consider the string to be part of the system, I guess the tension, I'll call this T1, and then I'll call the top tension T2, right? So these forces are acting on the boxes. What now? Just say this is M2 and this is M1. All right, so what now? So the force that makes it slide what do you mean by slide? I don't think there's any sliding happening. Over the pulley, okay. So the force that makes it slide opposes, like over the, okay. So the, so the force that goes this way, this is very informal notation. That's okay. The force that goes this way opposes tension. Right. And also gravity over whole thing. Radio. So this is a good idea. Then how would I translate this into, like, how would I set up an equation to actually represent like this statement right here? So actually, can I just say like a combination of the tensions and the gravities becomes the acceleration that we had? So M2 goes down and M1 goes up, right? And A is equal to G M2 minus M1 over M2 plus M1, right? And I'm going to just say that. So how do I make an equation that represents this? So you're saying that, like, let's break this up into parts. So T equals to, all right, let's slow down. So firstly, what is the force that causes the motion of the boxes over the pulley? Right, so this should be equal to, what should this be equal to? This should be equal to like M1 plus M2, which is the mass of the entire system times A, right? Because this force is causing your entire system, which has a mass of M1 plus M2, to move at an acceleration of A, where this A is equal to G times M2 minus M1 over M2 plus M1, right? And this turning force opposes the tension, which is just like T, right? So now, if I had a system and I wanted to analyze it as a whole instead of as like, separate things, then what point of interest is like really important the in considering the motion of entire systems? I think that's pretty important. Okay, the center of mass. Yeah, that's good. So if I consider the center of mass of the system of the two boxes here, so you have like these things, but then if I replace the entire system with this dot, then this means you have the force of the force of the turning that's kind of affecting the center of mass in a downwards manner. However, you also have the tension, which is keeping it up. You're keeping like the whole system up, right? And then so just like with this kind of thing, but then also like we know that the system has some sort of acceleration, right? So then this means we can say that the sum of the masses times the acceleration of the system is equal to the sum of the forces that are acting on the system, right? And this is going to be equal to T2 minus all the surrounding forces, right? Which is, I'm just going to say like the sum of all the external forces, sum of all Fx, right? But then now we have to find this thing because we don't actually know what this is. So yeah, does anyone remember how to find the acceleration of the center of mass of a system? Actually, yeah, Lewis, that's the correct answer, I think. Okay, so do you want to continue over, do you want to like preside over this conversation a little bit?
Um,
Like, were you here, first of all?
what?
Like, did you follow what we did up to this point, or did you do something completely different?
Um, well, I think I just basically used the force of like, or the expected force from gravity and the difference between like the sum of the expected forces from gravity and or the expected accelerations from gravity and the difference between those and the actual accelerations, and then multiply them by the mass.
All right. Let's go a little bit more into detail with that because that was kind of a rushed explanation, I think. So, hmm. Okay, let me digest what you said. Like you found the expected. Well, I think my method kind of formalizes what you said. Um, because the expected acceleration from gravity is going to be equal to like the two of these, but then you can take into consideration like this acceleration rate. So then, yeah. So what is the acceleration of the center of mass? I think this is a nice review question to ask. What's this equal to? Guys, come on. No, this is not parallel axis theorem. This is, all right, M1A plus M2A over M1 plus M2. Nice. Well, M1A2 plus M2, M1A1 plus M2A2 over M1 plus M2, right? But then we know the accelerations of M1 and M2, right? Because they're accelerating at the same rate, except one of them is going upwards and one of them is going downwards. So M1 is going upwards, that's what we assumed, and M2 is going downwards, so that's negative, right? And then, you know, if we multiply this by the sum of M, then this is going to be equal to like the sum of all forces that are acting on the sum of all forces that are acting on the system, right? And the sum of M times a com is equal to just, because the sum of M is just M1 plus M2, right? So then sum of all forces is just equal to like M1A minus M2A. And we said here that this is equal to, the sum of all forces acting on it. So is equal to the tension minus the sum of the other forces that are external to the system. However, what are the other forces that are external to the system? Any ideas here? Oh, by the way, I'm gonna just simplify this. So this is G times M2 minus M1 squared over M2 plus M1. And this is equal to G times M2 squared minus 2M1 M2 plus M2 squared over 1 plus M2, right? Yeah. Okay, so I'm going to flip a new page. So G times M2 squared plus minus 2M1 M2 plus M2 squared over M1 plus M2 is equal to the tension minus the external forces. Okay, the gravity and tension of both strings. That's good. So the other forces that are acting on it include gravity and tension, right? However, I'm gonna give you like a really nice way to sort of cut down on some of these things. So we were using the system as the two boxes, right? However, the string and the pulley do not have any mass, right? So if we change the system to include both the pulley and the string, what happens to the center of mass? Nothing happens to the center of mass, right? And also, what happens to the acceleration of the center of mass in that case? That also doesn't change, right? However, if we included the string as part of the system, then the tension can just be counted as an internal force instead of an external force. So now we can just like ignore that completely and we only focus on gravity, right? That's pretty neat. Internal versus, okay, um, so internal forces are forces that are applied to each other by bodies within a certain system. And external forces are forces applied by things that are outside of the system. So for example, um, like if I considered, like if I were pushing on two boxes, right? And then I applied a force to this first box. And I considered the system to be these two boxes, but not counting, the hand that I used to push it, right? So then, of course, there's going to be forces that are acting from one box to the other, right? However, because both of these boxes are within the system, then these two forces by the boxes on each other are not counted as external forces because they're completely internal to the system. However, the force that I used to push the boxes, this is an external force because the force comes from something that is external to the system. Okay, any questions? Net internal force would be zero. The net internal force, yeah, in this case, it would be zero. However, in many cases, it is not. So, and then, there's like something dynamic that's happening within the system. However, like, if you can find a good system where you can ignore as many things as you can, but also be able to solve the problem, that would be optimal, right? So system choice is important. Yeah. So if we made the system include both the ropes and the pulley, that makes tension and internal force, which means we don't actually have to care about it in our like force calculations because uh, Newton's second law states that uh, mass times acceleration is equal to like F net external, right? And this is the important bit of it. Okay, so now our system includes this entire thing, right? And the only external forces that we have to worry about is from gravity, right? So what is the force from gravity? So this is external, this is internal. Yeah, it's just m1 plus m2g. And this is actually all we need over here, right? We also have to note that it's negative because we defined down as negative. So then we have g times m2 squared minus 2m1 m2 plus m2 squared over m1 plus m2 equals to T2 minus negative G times m1 plus m2, right? And now, when you solve for T2, what do you get? Just take a couple minutes, or like a few, because this is just algebra. Please, please expand that and simplify. I don't actually think that's right. Um, yeah. Yeah, I don't actually think that's right. Um, okay, yeah, we have correct solution. Um, I'll just run through this. So algebra is hard. Yeah. This is equal to m2 squared minus 2m1 m2 plus m2 squared m1 squared over m1 plus m2, and then you have to subtract, well, you want this to have a denominator of m1 plus m2, right? So then you square this on the top. Yes, it is difference of squares. Actually, yeah, that's a simpler way to do it. So g times over m1 plus m2, this is m1 minus m2 squared minus m1 plus m2 squares, right? Yeah, because this is originally m2 minus m1 squared, right? And then you get, well, m1 minus m2 plus m1 plus m2, that gives you 2m1, right? And then you multiply it by a minus b, which gives you negative 2m2. And then that's all over m1 plus m2. All right. And then this becomes 4m1 m2 um, Yeah, 4m1 m2 over m1 plus m2 times g. All right. Any questions? Oh yeah, minus. So what does the minus mean? Well, it actually should be positive, but I'm pretty sure we just got our directions mixed up at some point because T2 is definitely supposed to point up. So yeah, we probably got our directions mixed up somewhere like in here, I'd say. Um, oh right, this is supposed to be m2 minus m1. That change anything? So if you add, you get 2m2. If you subtract, you get, hmm, or was this supposed to be negative? That wasn't supposed to be negative. Uh, I think it would change it if like, I don't know. We got directions mixed up at some point. Anyways, the magnitude is what matters. So what this means is that if you put this Atwood machine in a box, right? If we put this Atwood machine in a box and held it by a string, then the tension on the string would be equal to 4m1 m2 over m1 plus m2 times g, right? So this is also saying like the effective mass. Yeah, not if m2 is resting at the bottom. Yeah, but let's assume the we can assume the box is very large. I don't know. So this is to say the effective mass of the entire pulley box system is equal to 4 times m1 m2 over m1 plus m2 times g, right? And note that like this is not equal to m1 plus m2 just by itself times g, right? Yeah, assume string very long, sure. And yeah, and this is, which is why it's not the actual mass, because the actual mass is just m1 plus m2. But when you put it in sort of like this pulley system, it actually changes the like the effective mass of the system. So any questions on that? So like this would actually help us segue into the next part of this problem, which is the double Atwood machine. Right? So if I had a mass here, m1, but then on this thing, we have another pulley. And it has, and this pulley holds boxes of m2 and m3, right? So now in this case, recursive Atwood machine, yeah, kind of is. So now in this Atwood machine, like this rope is also going to have a tension. So now using what we already know about how, about effective masses, Like, what is T? Yeah, so take a couple of minutes. And of course, like there is a brute force way of solving it by labeling all the tensions, like T1, T1, and then T2, T2, M1G, M2G, M3G, and then finding like, you know, all the accelerations and whatnot. But I think that with this sort of insight, it makes it a lot simpler, right? Ooh, ugly expression. Yeah, the answer to this one is kind of ugly. Let me see if it's actually the correct expression. Okay, these seem like they're the correct answer. Oh, Ivan, you forgot a G, I think. Um, yeah, these seem correct. Anyone want to walk us through it? Who wants to walk us through it? Okay, I think you, is that the simplified version? Yeah, it is pretty ugly. Okay, so yeah, Ivan, do you want to walk us through it? Like, how do you get that expression? An
Okay, so
absolute
you
bulk.
plug it in.
Plug what in?
So in order to get the tension of the top one, it's you need the expression, um,
So I think the
which
first thing we need to do is put the right thing in a box, right?
yeah, and then you can get the effective mass of that.
Right. So then using this expression, we have T is equal to 4 times M1 times the effective mass of the box over M1 plus mass effective of the box, right?
hmm
And now, so what is the mass effective, the effective mass of the box?
The effective mass of the box is 4 M2 M3.
I am missing a G. Right, and then now
M2.
just plug this in everywhere, right?
Yeah, M2 plus M3.
Oh, you're right. Okay. And then from this I got t equals to just gonna copy from one of you. Why is there a G in mass? Oh, there isn't.
Oh, wait.
No, this is the effective weight. Yeah, my bad. There's no G. But there's a G in the tension. That's important. Yeah, you do divide by G to make it mass. Okay. So then after you plug this in, you get something along the lines of G times 16 M1, M2, M3 times M2 plus M3 over M1, M2 plus M3 plus 4M2, M3 times G. Something like this? Wait, why would you divide by G? Wouldn't you divide by the acceleration of the center of mass? Well, no, here's the thing. If I were to put like this entire system in a box, right? Then what I'm saying is by putting it in a box, the weight of the box is equal to the mass effective times G, right? Because that's how a box behaves. However, the mass of the box is not just equal to M1 plus M2 because there's something happening inside of the box that changes the effective mass, which is why the effective mass is equal to this expression that we have here, which is 4m1 m2 over m1 plus m2 times g, right? But then once we have this value, we actually can treat it as the mass of just a box, which is to say we can multiply it by g. So motion inside the box decreases its effective mass. Well, it can increase it, right? Is 4m1 m2 over m1 plus m2 always going to be larger or smaller? I don't think it's actually, I think it can vary. I'm not sure. You guys can do some math and figure that out. It's probably not too hard. Is there a way to get rid of the recursion? Well, that is kind of where we're going. So firstly, since it's 5:33, I will leave it here for now. This is pretty ugly, right? We'll leave it here for now, and then we'll have a 10-minute break until 5:43. All right? No, it's at 5:30. All right, so yeah, we'll see you at 5:43. All right. Hey, folks. Welcome back. Can everyone just put a hand up? All right.
Before we start, can I just make a quick announcement?
Yeah, sure.
So we've been in contact with some professors, and we managed to organize a lecture from a guest speaker from Stony Brook University. He'll be giving this talk probably sometime next week on Tuesday. So we'll probably have that instead of a meeting. So I guess if you want to come by. It'll probably be somewhere between 30 minutes to an hour with some time for Q&A afterwards. Yeah, so that's that.
Cool. Repeat that. Next Tuesday, there is a guest speaker. You'll be talking about, what is he talking about?
Geometry and topology in physics.
Yeah, geometry and physics. Very cool. So you guys should definitely stop by. Pretty interesting stuff. Yeah. All right. So let's continue on with this. So now that we have derived what happens in a double Atwood machine, in a double Atwood machine with 3 general masses, I want to kind of like generalize, or not generalize, like look at a specific case of it, where I'm not going to say triple, a specific case of it where all the masses are the same, right? Because like, I think that makes it a bit simpler. Because then here, this would be 4m squared over 2m, which is just 2m, right? So then this becomes, you know, and then here the tension is just going to be 4 times 2m times m over m plus 2m. Yeah, well, it is always in motion. Mm. And there's no motion. Yeah, but there's, okay, but then notice how when there's only 2, right? Then 4m squared over 2m, like this is exactly equal to the actual mass, which is just m plus m, right? So like there is actually no motion. However, it still works. So you understand what I'm saying? Yeah, okay. And okay, so going back to this becomes which is equal to like 8m squared over 3m, which is equal to like 8 over 3m. This is exactly where I am going. So yeah, now we're going to look at the infinite Atwood machine. All right, where I'm actually going to go to a new page for this. So the infinite Atwood machine, as you might guess, consists of, you know, a mass and then another Atwood machine with a mass and another Atwood machine, right? And then this process tends to infinity, right? So this goes all the way on. So then if there are like, let's say there are n pulleys, and of course there's a tension at the top string, right? So as n tends to infinity, what does t approach? Well, we're not going to really get into that. I'm just going to focus on this. But I'll look at that after if we have time. All right, yeah, so as n approaches infinity, or like the number of layers of Atwood machines, as that approaches infinity, what does t approach? All right, and then just as a reminder, I'm just going to put on this side. All right, so yeah, just take a couple minutes, try to think of some ideas. Like, what are you even supposed to do here when it becomes infinite? Uh, that is a very it does not have e in it. However, I can see where it's coming from. Usually when there's like something recursive, you might get some e, but no, it does not have e in it. It's actually pretty surprising because you might think it's infinite because there's an infinite number of masses, right? But it's actually like a fixed number and it's pretty small. Infinite pulleys on both sides would equal out to t equals mg. Well, okay, actually, yeah, I can talk about pulleys on both sides right now because if there are pulleys on both sides, then that means the entire system is in equilibrium, right? Which means that when it's in equilibrium, the effective mass is equal to the actual mass, and that's actually going to go to infinity. So we don't want that. Does that make sense, Arib? Yeah, and then when you actually have infinite pulleys, you will get infinite mass or tension. For what? What's 4 newtons of force? 4g. 4g. Why would it be a fixed number? I think you mean like 4 mg, right? Ivan, do you mean 4 mg? If so, like you're off. You're a bit off. Eh. Okay, wait, for 4g, the units don't work right because 4g is an acceleration and I'm asking for a tension. So it should be 4 mg, right? For 4g, the units don't work out. It does not go to infinity. And it does not touch the ground. All right, just don't worry about like touching the ground, okay? So like you guys should think about things you would do in other sorts of recursive problems. The pulleys do not get smaller and smaller. I just drew them smaller and smaller. Yeah, it does converge. Okay, all right, let's solve a different problem for now. Okay, we're gonna ignore this and we're gonna solve a different problem. So let's try to find the sum of like 1 plus 1/2 plus 1/4 plus 1/8 all the way up to infinity. So what is this? No, like I'm putting the pulley problem aside, and I'm just gonna 2. Yeah, okay, yeah. So this is equal to 2, but how do you get 2? Yeah, but like, do you guys know how like one would get 2 from this series? Telescoping? It's not exactly telescoping. Well, yeah, okay, geometric series formula. Well, yeah, but like without using the formula, how would you get 2? Like, yeah, okay. So set it equal to s, right? So s is equal to 1 plus 1/2 plus 1/4 plus dot dot dot. Well, this is assuming that it converges, but we know it does, so that's fine. Let's assume this converges. Well, you can actually prove that this converges using using like what's it called? There's like this convergence test that I forgot the name of, but like 1 over integer to a power always converges. Yeah, that is from BC. It's like, do you remember what it's called, Andrew? I don't remember what it's called. It's like the P test. Whatever. Anyways, so let's assume that S converges and it's equal to 1 plus half plus 1/4 plus dot dot dot. Harmonic series does not converge, if I remember correctly. All right, okay, uh, let's not dwell on the calculus. So if we assume that S converges and exists, now what? Yeah, okay, we take 1/2 S. Right, so 1/2 S is equal to, now if you multiply all these terms by half, then it's equal to like, then it's equivalent to multiplying the entire thing by half. So half plus 4th plus an 8th, dot, 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 right? But notice that this entire portion is just equal to this entire portion, right? So now we're not adding, we're subtracting. Now we take S minus 1/2 S is, this is just equal to 1, right? So that means half S is equal to 1. So S is equal to 2, right? So then this is like one of these infinitely recursing problems that where you can use the strategy of making a subpart equal to something else, right? You kind of relate the subproblem to the main problem, and then you connect them and you get your answer, right? So now how do you try to do something similar with the infinite Atwood machine? Substitute P of X on the inside. What's P of X? The effective mass of the final. All right, we're getting somewhere. Okay, so we can say because infinite, the right branch is equal to the whole thing. So because the effective mass times G is equal to the tension, okay. So like we have this, right? So then now we have to find the effective mass. So effective mass, so let this be the effective mass. All right. So if MF is equal, if the effective mass is equal, if the effective mass of this right branch is equal to the effective mass of the whole thing by our infinite recursion assumption, then this means that 4 times right times left over right plus left is equal to the effective mass. Yeah, this is equal to the effective mass, right? But then the right side is equal to the effective mass. And then the left side is just equal to small m, right? So we have 4 times mass effective times m over 3gn. What is n? Units. It should be 3mg. Because 3g doesn't work out in terms of units, because g is acceleration. It's not a force. Yep, there you go. Yeah, 3mg is correct, I think. Mass effective plus m is equal to the effective mass, right? Okay, so what am I going to do now? How do we know that this converges? That's a good question. I'll try to answer it later. uh, hmm. Well, let's proceed for now. Okay. So what do you get? Like mass effective squared plus m times mass effective is equal to 4 times the mass effective, right? So m effective minus 3 is equal to 0, right? So wait, did I mess this up? Oh, minus 3m. Yeah, okay. Did I factor right? I did. Okay. So then this concludes that the mass effective is equal to 3 times the mass of one of these little balls. All right. So any questions on that? Well, now I'm gonna like consider why it's actually bounded and like equal to like 3m. All right, by the way, tension equals to 3mg, right? Okay, so there's actually like a more rigorous method of finding why it's like 3m. And we're gonna introduce some more rigor. So if we look at the first couple of cases, right, with just 2 boxes, then the mass effective is equal to like 2m, right? And now if you do it for the second layer, this is equal to 8/3. 4 times 2m times m over m plus 2m, right? And then like, who wants to calculate the third layer for me? Shouldn't be too hard. For what's the effective mass for n equals 3? Guys? Okay. It, it shouldn't be m squared, it shouldn't be m cubed. It should just be like 16. Oh, that doesn't look right. I'll do it myself. Yeah, that looks right. It's like 32 over 11 times m, right? So like, just from these, we kind of see that it's tending towards 11, right? But how do we know that it actually tends towards, or it tends towards 3, my bad. But how do we know that it actually tends towards 3? Well, like, if we have some like beta times m, where beta times m is equal to the effective mass. So what are we doing with the effective mass to get to the next layer? What are we doing to get to the next layer? Times 4 on top times 4 minus 1 on the bottom. Yeah, it's equal to like 4 times beta times m over m times 1 plus beta, right? And then from beta, you go in the next iteration when you add 1 to n, for this you get for beta over 1 plus beta, right? So then, like, do you guys know that like the least upper bounds theorem, where like if a sequence is upper bounded by a number m, and it's monotonically increasing, then it has to tend towards that number, right? Do you guys agree with that? If it's monotonically, or if it's always increasing and it is upper bounded by some number, where that number is the least upper bound, then we know that the series has to tend towards that number. Okay, we're gonna make use of this. And we're gonna say like, if beta is less than 3, then the next iteration of beta, I'm gonna call it like f of beta, is also less than 3. Now we can actually just confirm this pretty quickly. So 4 beta over 1 plus beta is less than 3. So 4 beta is less than 3 plus 3 beta. And look at that, beta is less than 3, which is like correct, right? Which is follows from our assumption. And we do start with beta equals to 2, right? So we know that this is always going to stay true no matter like what beta we use. Like as we transition, it's always going to be less than 3. However, like the next part is that it's monotonically increasing. So then f of beta is always going to be greater than, or f of beta is always going to be greater than beta for all beta is less than 3, right? So yeah, you have like beta less than question mark for beta over 1 plus beta. So this is correct. Yeah. So we can first, we know that beta is positive, so get rid of one of these. Then we get like 1 plus beta is less than 4, hence beta is less than 3. This again is just the assumption that we made from the beginning, right? So from this, we know that beta of n is upper bounded by 3, and beta of n is upper bounded by 3 and is also monotonically increasing. And there's probably like some more rigorous method of like an epsilon delta proof for why beta of n, why 3 is the least upper bound and why it has to tend towards that, but I'm probably not going to do that. We'll save it for office hours. So what about that? Anyways, so this is 3, and this is what beta is, the constant factor on the effective mass, and this is like n, which is the number of iterations of the Atwood machine that we have, right? So we know that at 1 it starts at 2, and then it's just, it's just gonna get closer and closer to 3, but we know that it's never going to pass 3. However, it's gonna keep getting closer and closer, which is why beta, like when we take the limit as n goes to infinity, then beta of n has to be equal to 3, right? So yeah, this is why the mass effective tends to 3 times m, and the tension is equal to 3 mg. All right. Yeah, any questions? So this is the more rigorous way of proving that it actually converges to 3. But like recursion, just pure infinite recursion, if it tells you to find a value, it probably exists. So yeah, if you assume this exists, you can use this recursion thing. Otherwise, if you want to be more rigorous about it, you can use this sort of sequences argument. Questions? Yeah. Okay, so this was just a cool problem that I thought would be helpful in understanding center of mass and tension, some other stuff. Okay, we have like 15 minutes left. We can go over some F equals MA problems if no one has any questions on the last thing. All right, so for those of you who actually did the 2014 FMA, what questions did you guys want to go over? I think Andrew can help go over the problems, right? Yep, cool. So yeah, just drop requests, please. Should I leave if I don't want to hear the answers? Yeah, sure. I mean,
Okay, to those who have not done this F equals MA and want to do it, we'll see you guys next week. Come to the guest lecture if you want to. Please try to get the practice F equals MA in as soon as possible. We'll still check it over. But we we won't be able to do like this kind of problem solving thing again for the 2014 because we have to keep moving. So yeah, if anybody hasn't done it and wants to do it, we'll see you guys on Tuesday.
Right. And for next time, please do the 2015. I'll remember to put up a form this time.
Mm-hmm.
So 2014, 2015. Yeah. Okay.
Mm-hmm. So drop problem requests.
See you next week. If
Mm-hmm.
you guys want to, if you guys don't want to hear spoilers. All right. So drop problem requests.
And if you guys are quiet, then I guess, Alvin, do you have the graded stuff? Do you see like which problems cause the most trouble?
I forgot to I forgot to put out a form for this one. So unfortunately, no.
Okay. Well, you just tell me then which problems do you guys caused you the most trouble? At this point, just literally write any number from 1 to 25 in the chat.
Now, should I put the test link in the chat?
Yes, put the test link in the chat if to anybody who just doesn't remember the problems.
These are the solutions. That's not what I want. 2014.
Mm-hmm.
Yep.
Now we have enough time to do 1, maybe 2 problems. So like, chop chop.
19.
Problem 19. Okay, so let me read that problem. So, or actually, do you want to take a screenshot, Alvin, of that problem?
I don't think I can put it up onto the Zoom whiteboard.
I see. Okay,
Or
so
can I? And I just don't know about it.
okay, well, I guess I'll explain it. So we have a helicopter that's flying horizontally at a constant speed. So let me draw that helicopter. It's going to be a beautiful helicopter. That some say I draw the best helicopters. So boom. So this helicopter is flying horizontally at a constant speed, calling V. And a perfectly flexible uniform cable is suspended beneath the helicopter. And air friction on the cable is not negligible. So this is a situation where friction is not negligible. Just as a general rule of thumb for F equals ma problems, unless it specifically specifies friction in a problem, you can typically assume that friction is negligible. But here it says explicitly that friction is not negligible. Okay. And then which of the following diagrams best shows the shape of the cable as the helicopter flies through the air to the right? So there are 5 options here. So either the cable will just sit like this, completely vertical, or it'll trail behind him like this in a straight line, or it'll have this kind of curvature, or it'll be curved like this. And then the 5th option is it's curved like that. So you guys, can you guys tell apart the 5 different options, or should I put them in different colors? Let me put them in different colors. So this is the first option. Just a straight horizontal line down. The second option, let me just draw it in a thicker pen. Yeah, there we go. The second option is this. The third option is that. And the fourth option let's go pink, is this. And the fifth and final option, we'll have it be black, I guess, is this. So does anybody just have a preliminary guess? So preliminary guess, which one of these 5 options do you guys think is going to be the right answer? So do you guys think it's going to be A over here? This is B. This is C. This is D. And this is E. What would be your preliminary guess? Blue, C. Okay, why would blue be your guess? Torque. Well, nothing's rotating here, so it can't really be torque. So let's go through this problem then. So, okay, what we know, so let's draw this helicopter again. So here's our, let's draw a big helicopter this time. So here's our helicopter, right? This is F equals MA 2014, problem 19. There's air friction. C kind of looks like what happens when you try it with a paper. Yes, but you have to remember that with a paper, you have a second dimension, you have a surface. So surfaces, you know, you have a little bit of a problem because this thing has a length, a width, you know. Also, paper's not exactly flexible. But anyway, there's air friction on this cable, right? So if there's air friction on the cable, so then there has to be a horizontal component to the force where this cable is attached to the helicopter, right? Does everybody understand why that's the case? So type a Y in the chat if you understand why there has to be a horizontal component to the force at this attachment point. You guys are very quiet today. N, you do not understand why. Okay, so friction acts against motion, right? And in this case, it's going to be kinetic friction, right? Because you have this object moving, or you're going to have air friction. So you have particles of air bumping into this cable and dragging the cable. So we have, that means that this friction force has to be applied at this attachment point. All right, makes sense? Cool. So now, this part, again, you guys need to like understand why this next part makes sense. The idea with air friction is that the amount of air friction is proportional to the length of the cable hanging beneath at like literally any point on the cable, right? So the idea is, no, nobody says they don't understand. So you guys all get why it's proportional to the length hanging beneath the cable, right? This is why this is partially, you know, to your point, excuse me, Jeremy, on why it looks like C is the right answer, right? Because the longer it is, you know, the more friction, the less friction that there tends to be, right? So the further down you are, less you have. So because of this, because this air friction is proportional to the length of the cable, like hanging beneath at like literally any point, then that means that further down you go, the more you have. So it should be hanging like this in a diagonal straight line. But no, this is a problem, right? So why is this a problem? This is a problem because this is not how friction works, right? So this is actually very interesting because this question in particular, so it's funny how you chose this, Ivan. I think Ivan chose it. This question was kind of controversial on the ethicals MA because a lot of people challenged this answer because they tried experimentally and it didn't line up with the line of reasoning. So the general explanation for the correct answer is that the air friction on this object, on the hanging object, so hmm, hmm. I think I'm confusing myself here. mm,
Wait, okay, so like, what is the magnitude of air friction? Well, yeah, you might not actually know this, but at any point, uh, like for a particle traveling at velocity v, the air friction is given by like kV for things that move slowly, right? So the friction is equal to like kV. But then, like this point of contact with the helicopter, like this is always, it says that the helicopter is flying horizontally at constant speed, right? Which means that um, this point is always going to be traveling at a velocity of some v, right? And then it's going to have some frictional force, but that's not going to really matter at the top point. However, as like the intuition is like, I think as it goes further down the string, the as you go further down, like there's going to be the same frictional force going in the left direction all over. However, there's less of an impact on the actual, like, there's less of a bearing. The top point has less of a bearing on the bottom point because it's like, it's further away from this part, which has to go at a velocity of v, right? And like, also because this f is linearly proportional to v, then like this dependence is also going to be linear in proportion. So then, which is why, as you go further down, the actual effect it's going to have, like here, friction has zero effect, right? But at the bottom, it's going to be like, since the bottom isn't even like there to stop it from doing anything, it's going to have like its full. And then this dependence is linearly proportional to the length or the distance away from the contact point. So then that's why the rope becomes like straight, right? However, I don't know, I was kind of confused by this problem as well. And
So, oh,
and
sorry, go ahead.
this is what I was thinking, right? And then the solution also was a bit
Complicated. So
just
yeah, the idea with the solution or with the different solution methods is that the answer is different if a mass is hanging from the end of this cable. So if you had like some sort of mass hanging at the end of this helicopter cable, then the answer would actually be D, right? Because this thing would have a greater vertical component for gravity than any other point on the cable. And so it would be less affected. It would be dragged more by this friction because there's a greater inertia at the bottom. So it curves like this. But because that's not the case for a just cable, then it looks straight. That was the general discrepancy.
well, and I think like the reason why it's not C is because it implies that friction has a quadratic dependence on V. However, it is true that for very high speeds, it is quadratically dependent. However, yeah, the question doesn't really say anything on how fast the helicopter is going, which I think is why this question is like very heavily disputed. Weird air friction problem.
Yeah, we're kind of at time, so we don't really have time to talk about any other questions. But please, 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 please do this contest if you haven't done it already.
Yes, come to office hours if you want to talk about the questions.
Yeah. And yeah, stay tuned for more detailed logistics regarding the talk next Tuesday.
All right. Goodbye, everyone.